Hello, everyone. Welcome to our first webinar in series organized by the Technical Committee on Bio-Nanotechnology and Biomems under Engineering and IEEE Engineering in Medicine Biological Society. Let me introduce myself first. My name is Levent Yobaz. I'm with the Hong Kong University of Science and Technology, Department of Electronic and Computer Engineering, and also joint appointment with the Department of Bioengineering. And our first webinar is to be given by Professor Pavel Neužil. Let me give you a brief introduction about Professor Neužil. He obtained his PhD at the Czech Republic, Czech Technical University in Prague, Faculty of Electrical Engineering in 1995. I believe he worked at various universities and institutes, including Stanford University, and also Institute of Microelectronics and Institute of Bioengineering and Nanotechnology in Singapore. Currently, he holds an academic position at, I hope my pronunciation is correct, Brno University. I hope
Technology.
Brno University Technology, Czech Republic, as well as Northwestern Polytechnical University in China. His earlier work concerned with the electrical engineering and planar CMOS technologies. During the last 2 decades, he has focused on chemical, physical, and optical sensors, as well as medical devices, including portable systems performing polymerase chain reaction. This brings up to the topic of today's talk, which is quite timely, a miniaturized PCR system for the diagnosis of COVID-19 and other infectious diseases. Without further ado, I'll pass it to Professor Neužil for his interesting talk. Please, Professor Neužil.
Okay. Thank you, Prof. Levent, for the introduction. And as you said before, so my work in last maybe 18-20 years was linked to microfluidics for clinical diagnostic mostly, as well as similar devices in that field which are linked to it. Where's my laser? Here. Good. So first, would mention something about clinical diagnostics. I believe this 100% be sure that everybody knows what that is, and especially due to COVID-19 pandemic. So what we do, we are from typically body fluids. And please do not mix it with a device of type called a tricorder from Star Trek, because tricorder in Star Trek, you put it on skin, you get a list of diseases you have. It doesn't work that way in real life. Clinical diagnostic system works way. We are looking for very specific disease, and if the test is done correctly, you get answer yes or no. But you don't get a typical answer taking your sample and get 20-30 different diseases. One of the key system which is used is called polymerase reaction. I talk about it a little bit later, but you can see how it goes. You get sample, you mix it, get this here is magnetic particles, get system DNA out or RNA, and eventually perform polymerase reaction for DNA. For RNA, it's which is a COVID-19, SARS-CoV-2 RNA, you need to do reverse transcription PCR first. Some 30 years ago, there was a new field was developed called lab on a chip, and it was actually introduced or made popular by Professor Mans, and the time from Imperial College in London. And his vision was, as you can see here, that entire lab can be shrank into small chip. This one is few centimeters by few centimeters size. In early days, this was not really lab on a chip, it was more chip in a lab. Because even chip was small, no problem to make it small. This is 17 by 17 millimeter electrophoresis chip. This is small size. We have it even here somewhere. What is it? And but the problem was that you need the chip is here. You can see the size of this device here. You can see it now. Like 2 centimeters by 5 centimeters from the ADAS laboratories in Singapore. Problem was that you need a lot of equipment for fluorescent, which we use very often. You need blue laser. At the time, the available laser was 20 kg heavy, water-cooled system. So in order to use this small chip, you need half of the room filled with equipment. So it was more like, call it chip in a lab, which of course people who came with this idea, they don't like it very much. Nevertheless, in development of in the time of development, things getting smaller and smaller, and currently I would say we are approaching that lab on a chip quite closely. With PCR, to say, because PCR is key system we are dealing with, and show history was developed by Kerry Morris. He died last year, and it was published in '85, and he got Nobel Prize for his invention. And interesting thing about his invention of polymerization reaction, explain what I mean, is it is specific multiplication of DNA sequences. Interesting thing was that Dr. Morris, in fact, did not, if I say very bluntly, did not like invent anything. And I'm not downplaying his work, because his achievement is absolutely tremendous. It changed life of many people, including even like created new sciences. But what he did was very interesting. He combined known steps. So he somehow didn't invent PCR, but by adding known steps together in sequence and cycle, he created absolutely fantastic system for polymerization reaction. And it was Tech Polymerase was declared Molecule of the Year, and also PCR itself is considered one of the greatest discovery of last century, and rightfully, I would say. But the interesting thing is that even molecular biologists working with Dr. Morris failed to understand what can be done with it, and how absolutely fabulous this invention is. Took a little bit to find out, and for information is quite interesting. His company, Cedars Corporation, gave Dr. Morris award for his work, $5,000, and they sold patent for about 5 billion or 3 billion, I don't know how much. So definitely he didn't get that much. But it doesn't matter. You can look at it. A PCR is basically chemical amplifier. So in time, you increase concentration of, in our case here, of DNA, or number of copies of sequence of DNA you're looking for, so much that you can detect it. I mentioned this is a highly specific biological biochemical replicator of DNA. and works the following way. You get double-stranded DNA. You heat it up to temperature of denaturation, where the double-stranded DNA molecule will cleave into two single-stranded molecules. After that, you need to have specific primer called short oligonucleotide, but you can also say short sequence of DNA specific to the one you are looking for. So one is forward, one is back, reverse primer. So if this DNA exists in the solution, primer will anneal to it because it complemented this part. The other primer will anneal here. Next step is elongation. You heat it up to 72 centigrades, and in presence of Mg salt, buffers, dye, polymerase, and 4 nucleotides, ACGT, it will finish the sequence. And next step is again denaturation, use cleavage again, and so on. So this is one cycle of PCR. As you can see, after that one cycle, you get from one molecule of DNA, you get 2. And after another cycle, you get 4, 8, 16, 32, and so on. And we typically run 42 cycles, sorry, 40 cycles, which means in theory 2 to the power of 40. There was applications. Also, applications, there is many of those. Yeah, you can you remember, I believe, Jurassic Park. They're also detecting DNA. You can do sequencing, detect mutations, forensic analysis, like which is, for instance, in a crime scene, when there is some sample, biological sample, we can find out based on chromosomes, X, X, Y, presence, man or female, or also animal or human. Find out also paternity detection or proving, so comparing sequence of potential father with sequence of child, we can prove or disprove that if the father is a man is father of the child or not. And NIPT is another one, which is non-invasive prenatal diagnostics. And this is like detecting from mother blood, detecting potential genetic diseases of child, such as Down syndrome or Richter syndrome. And while back, when I was working in biology and nanotechnology, that time was a problem of which could turn into pandemic, was avian flu. And we decided at the time to develop system which would be portable, easy to use, and be able to perform molecular diagnosis. So it has to be efficient in comparison with commercial systems. Battery operated was also important, because at the time we assumed somehow that it should go to rural area of Indonesia and other countries like Philippines, and you cannot assume that power is always available, except one which does exist practically everywhere, and which is 12-volt battery, because it's a car battery and cars are practically everywhere. So regardless how reliable is normal 230, 220 or 110-volt network, 12-volt battery is practically always available. Should be easy to operate, economical, portable, and ability to detect RNA, which means perform RT-PCR. One thing which was important part has to be disposable. And what has to be disposable is anything which gets into contact with DNA or sample containing DNA, RNA has to be only one-time use. And it's very simple, because we discussed it with doctors, and even our background is um, silicon chip manufacturing. We believe we can clean our microfluidic systems that no DNA can survive, but doctors don't believe it. So doesn't matter. It has to be this no recycling, so disposable. So we came up with my coworker back in IBM is called virtual reaction chamber, VRC, where a sample is placed on glass, which is microscope cover slip, and covered with oil. And this cover slip is sitting on silicon chip, which has here heater and sensor. So we can use closed feedback loop system to control temperature inside. And PCI is conducted on a disposable glass, which is coated with fluorescent. So once the PCR is finished here, we take glass, take away, put new glass there. So we fulfill that requirement. This surface is disposable, and at the same time, it's quite nice because the glass is cheap. So we develop a system based on micro machine on silicon, where there is heat sensor I showed before, and this is photograph of actual chip, 24 by 24 millimeter big, with cover slip here, 12 by 12, so 22 by 22 millimeter glass. And here are 4 samples. Actually, it's not sample, it's ink, blue ink for contrast, so it's nicely visible. For heating, we use PID controller. For cooling, we have passive cooling, just switch it off, and cooling is done by time constant. So before actually making those chips, we did final element analysis of the system. This is photograph, infrared image, and this is ANSYS model of the system showing basically crosstalk between samples here, which is not much, and very similar is shown here. So we can see glass here. This is a gap in between, and this is a chip. So this is infrared image using camera between operating between 8 and 14 micrometer wavelengths. Infrared camera. We developed 2 systems. One is we call it Micro PCR. One we call Nano PCR. And difference is this is taking small sample into account, and it's faster because sample is smaller. So we have to either for 2 versions. We have 4 chambers here and 10 chambers here, but typically we run only one for practical reason. Here are some parameters. Oh, that's interesting. It should be ohm here. Why is W? I think maybe we did copy paste. We converted ohms into W. Doesn't matter. So there are some parameters. Important part is here because heating is 50 Kelvin per second for the micro system, and nano is 175. And cooling, more interesting, is because it's more difficult, minus 30 Kelvin or minus 125 Kelvin per second. And it was cited in 2007 as world fastest PCR. These days it's not true anymore, because 2017-18, Carl Whitworth from University of Utah, he published called Extreme PCR, and he is able to run 1 cycle in 0.6 seconds, so which is fantastic speed and basically unbeatable. Unbeatable from the sense that even we could make it faster, but doesn't make any reason. There's no reason to do it, because if he made 0.6 seconds, we made 0.55. That the difference is so little, there is no point of doing it even. Okay, fine. So we have done this. Then we move further, and we start measuring fluorescence from the sample. Interesting, somehow behaving funny way. Okay, so this is called this different temperature, And we normally, when you run PCR, you get this curve out. But here we get many more points. And at the end of it, we run melting curve analysis, shown here. We increase temperature and measure fluorescence. And minus dF over dt as function of temperature gives you peak. And you are watching if this peak is at correct temperature, means that this PCR was either specific amplification or non-specific. And this is first test how to find out if the temperature is correct. Highly likely it was specific. And then you should also run once in a while electrophoresis to just look how many base pairs you have product, PCR product, and if it's correct number, that means that PCR was specific. Then we run a smaller system. We got 40 seconds, 30 minutes. As I said, Carl Whitwell is able to do it in about 30 seconds now. So it's just pretty much faster than we. But okay. And biosynthetic quantum chemistry, two-step PCR only. And here you can even see like how the fluorescent developing, which is monitoring this curve here, which is fluorescent during annealing elongation, tells you that here the system is already finished. There is no need to wait to the end because no more amplification will happen. And the same way, if you go to cycle somewhere here, you will find out that it's not finished yet and we stop it prematurely. We also did RT-PCR using for avian flu that time, H5N1, and it was quite fast. We did RT-PCR in about 12 minutes. But the issue was funny there. We use microscope to detect fluorescence, which is fine. We have visitors. We showed them our new PCR system, which is here, and they always ask, so, and what is this thing here next to it? Well, oh, that's microscope. We use it to detect fluorescence. How much is it? About $30,000. So they say, so I was saying that in order to use this marvelous PCR, you need $30,000 microscope. What is this good for? So next step was integrating optical module and switching from this set here into something much smaller. And you can see it here. So we got inspired by DVD pickup head. You look inside how it's done, the mechanics, and simplify it for us. So you can see it here, blue LED. Here is collimating lens, blue filter to clean the light, bounce off by dichroic mirror, normal mirror to the focusing lens, like shown here, and to the sample, generating fluorescence, collecting, bouncing back, getting pseudichroic mirror, green filter to block blue light, and into amplifier, which amplifies about 5 times to the power of 6 to get a stronger signal coming out for further processing. This is schematically shown how we did heat temperature controlling system using some circuit which giving some sinusoidal signal, Wheatstone bridge, and multiplication using local amplifier to get high signal to noise ratio system. And heating we use just also modulation system. So by switching MOSFET transistor and on-off heater. This is more important and more complicated also. We use a blue LED here and AC powered. We have some signal here, about 1 kilohertz roughly. Photodiode, low noise amplifier, capacitive coupling, normal amplifier, and 2 local amplifier. And we have signal amplification with 10 to the power of 8. Very strong. So what you see here, you have 3 generations of PCR. The first one, which is only 1 sample, second one, 2 samples is nicely on display, and third one, 4 samples, which is complete system working nicely. So for the first generation, we got RT-PCR for avian flu. So you can see normally we get data are like this curve here. Curve is shown here. And critical threshold is telling you that A, the RNA we are looking for was found, B, how much of the RNA is there. And at the end of this process, we perform again a multi-curve analysis to find out if that temperature is correct and it's practically identical it should be. So we can assume this system is show specific amplification of RNA. Then we decided to go for a second generation, which was combination of different LOC techniques. And so we had lock-in amplifier as a key part of it. Everything is the same for regardless what technique you are using. So you're using temperature controller, some CPU, high voltage power supply, stepper, battery management, communication with PC for programming, and some touchscreen LCD. And we decided to have different system, electrochemical, nanowire, localized surface plasma resonance, and PCR in space domain and in time domain. What does it mean? Time domain means sample is located is at one location and we change temperature of that location. Space domain means areas have fixed temperature and sample is moved between those areas. Both have advantages and disadvantages, of course. So core of the system is shown here. We use 4-channel lock-in amplifier, different frequencies. It goes up 4 channels, either via attenuators to electrochemical cells or nanowires, and then amplifier, or here 4 different LEDs, 1 photodiode, and again amplifier. And here we have 4 lock-in amplifiers. We can split the signals again from each other from one composite signal from here. I will skip this part because it's not interesting. So we have done PCR. This is another type. LSPR. This is a chip made back in ISO microelectronics. Change color with different fluid. So when we are changing, this is water. This is ethanol. And we have different reflection from the surface in water as well as in ethanol. So we also serve nanovirus, and plus this one was quite okay working, but there are some basic problems with nanovirus, so eventually the project was stopped. And another one was electrochemical sensor, which we did some testing with. So this second generation is flexible design, which is very nice. You can have many different things detect, and it's very versatile, but it's too complicated. And a while back I said this is questionable necessity of a modular LOC system. And what I mean here is following that very often laboratories are specialized to certain areas, and laboratories specialized for DNA does not work too much with proteins and vice versa. And if they do electrochemistry, they typically don't do too much PCR or vice versa. And I'm not saying there are exceptions. Definitely there are exceptions around the world, for sure. But we decided that it was just too complex. So let's do it simple way. And we decided to create third generation of portable PCR systems. Few issues. Has to be simple. Has to measure 4 samples concurrently. And reason is very simple, because this is how it should be done for COVID-19, for instance, that you should always negative sample and negative control. And negative control typically is that instead of sample, use water. Positive control, you are adding RNA of the virus you want to detect. And problem is, okay, for COVID it's not that big problem, but for other diseases like HIV, for instance, is very social problem. If a doctor will tell HIV patient based on false negative, saying that the patient is actually not positive, it would not be true. So the patient can spread the disease, which COVID of course also bad, or false positive, telling a negative patient that yeah, he's HIV positive. It's also no good. So what we need to do around always negative and positive control, and plus 2 samples, so we have 4 total. Small size, palm size, and perform RT-PCR in real time. This is also important for another reason. You can do some, of course, very classical PCR with detection of the product using capillary electrophoresis or hybridization, but that is complicated because typically you have to take the sample away from PCR, move somewhere else. But doing real-time PCR, RT-PCR has advantage that we are measuring a product of the reaction during the reaction itself. So when we are finished, everything is finished. Plus the data. So this is how it looks like. You have a small system, very palm size, because it sits in somebody's hand. Inside, what is there is blue LED, blue filter, bounce of the acrylic mirror going up to the sample, which is heat up or cooled, generate fluorescence, then go down through the acrylic mirror, through green filter, and to photodiode, and process signal is processed. You can see here, there are 4 samples, and after PCR is over, you can get 4 curves plus negative control. 1 is negative control, 2 is positive control, and 3 and 4 are samples. This is what is inside. Simplified version. You have 4 heaters controlled by MOSFET driver, and there's also temperature sensor here with in bridge, connect to local amplifier. And only 2 seconds in each cycle we are measuring fluorescence. That moment this switches from temperature to fluorescence, and each photodiode, each LED will blink for 0.5 seconds. During that time, we can get signals here in sequence, and then processed by MCU. So first we are testing Ebola, RNA of Ebola virus after avian flu with GAPDH housekeeping gene as reference, and as are the results. So we have, of course, we use a sample. So black is combination GAPDH plus Ebola, that is GAPDH only, and green is only Ebola. And TC is blue. Which is showing that sample is uncontaminated. Okay. So after that, we also run melting game analysis is shown here, and after processing is here. So showing that the peaks are at correct temperatures means this amplification was specific. And we also did the avian flu. What we add, the version 2. Version 2 is a little bit more advanced than version 1. And we have extra that this chip is replaceable. So if it's damaged, we can just unplug it and plug it back, plug a new one. And we also modify the software. So now it communicates via Bluetooth with cell phone or smartphone. And we can program it from PC or from phone, just type in numbers and send by USB or Bluetooth into the system. Then we created Internet or part of Internet of Things. This is not actually real testing. This is emulated or assumed that if there is like dengue fever outbreak in Xi'an, we will be going with similar system around Xi'an, perform testing, and here is hospital, so we will automatically via phone be sending information to hospital in the monitoring center. And interesting enough, this happened, I think, in December last year. We published this work, yeah, and in January, COVID-19 started. So actually started, in fact, end of December. So it was very timely, except we assumed something like dengue fever, and it was not dengue, it was COVID-19, as you know. And I would say, conclusion of this generation, we had we measure small system, which is 100 by 60 by 30 millimeters, weighs about 100 grams, and few watt power consumption, can perform for PCR, and we this is for Ebola as well as dengue fever. And now it's becoming part of the system for sample to answer for COVID-19, which we are developing.
Okay. Thank you very much.
I would stop it here because the rest is, yeah, I don't want to bore anybody too much. There are some more details about our work. So thank you for your attention.
Okay, thank you very much, Dr. Neužil, for this impressive presentation, actually impressive PCR. I can see that it's quite compact and small, that fits into a palm. So maybe I might have a question regarding any commercialization efforts, because given the current pandemic situation, I think such a product is really what we need. Quite helpful. So I wonder whether you look into commercialization aspect, and you have any comments on that aspect.
Yeah, sure. Thank you. It's a slightly complex issue because key part of, as you know, key part of any PCR system to be commercialized for like COVID-19, for instance, is sample preparation. And without sample preparation, this PCR itself cannot stay on its own. And there is quite, I would call it a race to develop it. Quite a few number of companies claim they have it. And I don't want to name any company, but one quite well-known company claim they have it. So we try to buy it. Problem is you cannot buy it because obviously they don't have it. They just had nice presentation and about that work, how they believe it might work in future. And we back in so microelectronics, we have this statement. We call this PowerPoint technology. So many of those systems they work beautifully in PowerPoint presentations, but when you want to use them, it's very different story. And it's not a laughing matter. It is complicated because whoever went through testing of COVID-19, I went through it like 20-25 times, and it's always very similar. They take sample, put it into vial with like 2 milliliter solution, and they need somehow get COVID virus from this 2 ml into volume which PCR can be done at. And PCR is typically done at a few microliters to 20 microliters. So somehow you need to get from big volume of 2 milliliters reasonable amount into that 10 to 20 microliters. And this is another headache. There is, for instance, one company. I look at FDA, or the Food and Drug Administration of United States of America, and there is list of approved systems, and one of them has a limit of number of copies 600,000. 600,000 copy number as a limit, LOD, is not system, is joke, because it's so high that basically you can almost see them. Okay,
Mhm.
so system like that doesn't make any sense. So you have to get somehow pre-concentration, because in microfluidics you have to deal with small volume, and you start with big volume and you need to fish out most of the RNA or reasonably big amount of RNA into small volume. And I think it's a key part, and we are working on it, as many others, of course. But it's a difficult job.
Yeah, I totally agree with you on that one. I think sample preparation is the really major bottleneck, and I've been following this area quite some time also, and I think there's no really one good solution that addresses this issue, sample preparation, and also integration with the subsequent PCR.
Mhm.
But I think the PCR part is quite a bit developed compared to sample preparation. I think sample preparation is a bit behind, lagging. Uh, but it's a bit pressure on our community, I will say that, because we started with PCR, capillary electrophoresis on chip. Uh, that the idea of lab on a chip concept. I think when we face these epidemics like avian flu or current pandemic, I think that kind of putting us on the spotlight basically to deliver such systems for screening the masses. I think we this is a bit really
But
critical for us.
you can also see it positively, because 2 years ago you would ask around what is PCR, and you will see like this quite empty face. Basically, nobody ever heard of it. You ask these days, everybody knows PCR. So certain way, it also helped our community, because exactly putting us on spot, which is you have to do something, but also people start understanding that it makes sense. It's not just some silly scientist spending public money playing and basically wasting resources for some nonsense. Okay, so certain way it did help microfluidics quite a bit, and PCR development, and also public awareness of the techniques and technology.
Well, um, okay. I think this was quite uh, uh, quite interesting talk. I would like to thank Professor Neužil one more time. I hope we will further visit this topic in the following webinars. Um, um, and I'd like to, I think, conclude our webinar now, and see you in the next webinar.
Thank
Thank
you.
you.